Morning, everyone. Thank you for coming. This is a short lifespan for a regular mass. Welcome to CppCon. It's still the second day of the conference. New venue, the same great conference. I know I've been to every CppCon so far. How many of you are first-time attendees? Oh, quite a few. Cool. So, do we like the new venue? Yeah? Well, ever since I arrived here, this angle has been bothering me. And I know I keep worrying about the little details. I don't think that locomotive is going to fit through that bridge there. I'm really worried that might wreck something. And now every time you pass through there, maybe you obsess about the same things. Okay. We should maybe file a formal complaint to the managers here. Let's get back to our business. Lifespans, lifetime of objects, and regular types. Has anyone seen any of the 3 versions of my previous talk on regular types? Yeah, I see a few hands. Okay. For those of you who haven't seen it yet, I'm going to go through a bit of the part 1 that we've covered in the other talk, and I'm going to cover a few fundamental details, a few theoretical things, and then we're going to build on that to examine new facilities, and we're going to examine how concepts are defined in the standard, and we're going to cover the design and evolution of some new library facilities like string view and span, and see how designing these types by designing these types together as a community, we're thinking about the fundamental concepts of our programming field. And we'll see how examining mistakes and improving on them is going to help us build even better library facilities in the future. So why regular types? Why are we talking about this? Well, it's not just about regular types. It's a moment to reflect on STL and its design principles, as best described by Alexander Stepanov in his seminal paper from 21 years ago, Fundamentals of Generic Programming. And we shall see that regular types naturally appear as necessary foundational blocks in programming, and we will try to investigate how requirements on types fit in the design and evolution of the standard and of the standard library, of its data structures, and of its algorithms. So we're going to talk about values, objects, concepts, ordering relations, requirements, equality. We're going to spend some time on equality, whole part semantics, lifetimes of objects, standard span, of course, as a prime example for our analysis, CPP core guidelines. We're going to talk about C++ 17 features, C++ 20 features, and why not the future? We're going to talk about what it means to build modern C++ APIs, and we're going to talk about types and how to build type families and the properties that we need to think about when designing types and vocabulary types and interfaces. I do recommend that you watch at least part 2 of this 2-part series of talks by Titus Winters from last year's CppCon. But let's start with the beginning. About 2000 BC? No, not quite. I'm going to take you through 3 algorithmic journeys. I do recommend, this is a very lengthy series of lectures by Alexander Stepanov that he gave at A9. And they cover a wide spectrum of mathematics and evolution from Egyptians and Egyptian multiplication and GCD algorithm up to the 20th century. And it's quite a long series. As you can see, we have like over 30 hours of content there. I binged it like a good Netflix series. If you cannot do that, at least read this book. It's not that big. So this would be the condensed version of that series. And I think it's a foundational book for our field. It will help us understand why we should think about programming concepts in terms of mathematical foundation. And I'm not talking about category theory or abstract algebra or a billion groups or what have you. I'm talking about a rigorous mathematical logic and how we can create building blocks with which we can analyze and construct our abstractions. So in the beginning, there were just zeros and ones. So we call that a datum, a series of zeros and ones. And a value type is a correspondence between a species, abstract or concrete, and a set of datums. A value is a datum together with its interpretation. So a series of zeros and ones with an interpretation function. For example, int 32 as 2's complement big endian is a value. And the value is an abstract thing. It cannot change, like value 5, the same. And if a value is uniquely represented, equality means representational equality. And if a value type is not ambiguously defined, representational equality implies equality. We shall see that this is an important aspect, and in many situations, properly defining equality is not such a trivial thing. An object, not in terms of object-oriented programming, but in terms of von Neumann machines, is a representation of a concrete entity as a value in computer memory, given by its address and length. And an object has a state that is a value of some type. And of course, that can change. A type is a set of values with the same interpretation function and operations. So that's how we define the type. And a concept is just a collection of similar types. They share some properties. All these definitions are lifted from elements of programming. How many of you have heard or read elements of programming? Quite a few hands. More than I expected. Yeah, that's a good question. That's a good question. As a disclosure, I keep, the question was how many people actually finished the book. So as a confession, I keep it on my desk. So I keep reading it. So it's that kind of a book. Fortunately, starting this year, it's a free PDF available from the official website. So you can get it in electronic form. And it's much nicer because you can search for things in it and copy-paste and send references to book chapters. Yes, mathematics really does matter. And I do recommend that you watch this presentation. I think it's, in my opinion, this is the most powerful presentation by Alexander Stepanov. It covers a very simple concept, the GCD algorithm, but the journey that it takes you through over 2,000 years of mathematics and the evolution of the human understanding of abstraction and logical concepts is a wonderful experience, and I highly recommend that you watch it. But you may say that this talk is too theoretical, too much mathematics. I don't need that much math to program. So the reason that things just worked for you is that other people have thought long and hard about these concepts and the details of the type systems and the libraries you're using, such that it feels natural and intuitive to you. 4,000 years of mathematics leads to this paper that I consider foundational for our programming field in C++ and not only, fundamentals of generic programming. And Alexander defines generic programming as depending on the composition of programs into components that may be developed separately and combined arbitrarily, subject to well-defined interfaces. Among the interfaces of interest, the most used are the fundamental operations common to all built-in types, as extended to the types we define. And he makes a very strong point on how rigorously we can define equality. We must investigate relations that must hold between these types, and we must ensure that operations that we defined are consistent with the expectations of the programmers. For example, if we define less than or equality for our types, they should not have unexpected meaning as opposed to, for example, integers. In other words, we want a foundational powerful enough to support any sophisticated programming task, but simple and intuitive to use and to reason about. But is simplicity a good goal? We're C++ programmers. We like complicated things. Well, I disagree. I really, really, really hate when C++ programmers brag about understanding some obscure language construct or syntactical construct as if they discovered the fundamental laws of the universe or something. Simplicity is a good goal. Simple code is more readable code. Think about code reviews. Think about onboarding new hires. Think about teaching. Unsurprising code is more maintainable. Code that moves complexity to abstractions, like libraries, are easier and have to use and have less bugs. Compilers and libraries usually do a great job. Yes, they do have bugs, but they usually are of good quality, and you can count on many people testing and using those libraries and helping improve them. So it's better than rolling your own. And simplicity is an act of generosity to your colleagues and to future you. I'm going to point you to a relatively recent paper by Titus Winters on revisiting regular types. And this evokes the Anna Karenina principle of designing C++ types, in that good types are all alike, bad types, poorly designed types are poorly designed in their own way. So I like this paper. I've read it like 3 times already while preparing these talks. And if you find that the original Stepanov paper is more, it's not long, but if you find it more difficult to follow, or if you have the opinion that it's not rooted in modern reality, this essay, I think it's a much more approachable starting point for this kind of analysis, and helps you build understanding on fundamental principles, and it gives you concrete examples to modern constructs, and it helps you understand the rationale behind the original Stepanov paper. Yeah, and you do have references to string view and span there. So let's get back to the roots, STL and its design principles. If you want the manifesto, so to speak, this would be the first talk that I think Stepanov gave in the 90s, no, in the early 2000s, on STL and its design principles. So if you want the manifesto of generic programming and the STL as a library, quite young back then, you should watch this talk. So fundamental principles. I'm going to synthesize the contents of that talk for you in a few slides. Systematically identifying and organizing useful algorithms and data structures, finding the most general representation of algorithms, hence generic programming, using whole part value semantics for data structures. We're going to see what that means. And using abstraction of addresses, iterators, and ranges to interface between algorithms and data structures. For example, plus, multiply, min, max are associative operations. And because they're associative, you can reorder operands, and you can parallelize them and use reduction. For example, algorithms like accumulate or transform reduce. And these kinds of properties and these kinds of operations and their lifting operations, their abstractions, their generalizations, come from abstractions in algebra, in mathematics. And yes, as Sean Parents likes to say, there is a generic algorithm behind every while and for loop. STL data structures extend the semantics of C structures in terms of layout. And two objects never intersect. They should have separate lifetimes. And they are separate entities. I think this is the part where we most frequently fail when we design types. We sometimes forget to properly define the composition of our objects. And our dependencies sometimes come back and bite us. Whole part semantics, when you copy the whole, you copy the parts. Sounds intuitive, but it doesn't work for all types. When the whole object is destroyed, all the parts are destroyed, and two things are equal when they have the same number of parts and their parts are equal, corresponding. Generic programming has some drawbacks. It's not all roses. And I think the most painful that we every day experienced is the horrible error messages from our template algorithms. And yes, we're going to get concepts and requirements on types and that these algorithms work on are going to help a lot. But until then, the burden is on us to understand the requirements of the algorithms we use and we design. Some examples of named requirements would be these. Named requirements are used in the normative text of the C++ standard to define expectations of the standard library. Some of these requirements will be standardized as C++20 concepts. But until then, the burden is on us to define and to ensure that the algorithms we use and we consume satisfy those named requirements. So we need to check the documentation and make sure that we're in agreement. It's like a contract, so to speak. A concept is a formal specification that allows the compiler to verify these template arguments, to verify that they match these predicates. Concepts are predicates, and they can be checked at compile time. They can be composed, and we will get a much friendlier error message that is presented in the interface that we use, not manifested in the implementation of a particular function or algorithm. So with C++20, we're going to get concepts. And yep, they've been renamed to snake case, in case you didn't know. And my personal rant here is that adults don't have imagination. I like the camel case notation for concepts. I know it's not a popular opinion, but I have the stage now, so I get to rant. And the paper proposing the renaming actually articulates very well some of these reasons. And I like the original notation because I think it's desirable to make them stand out, because I think there are policies rather than types. And not being types, my opinion, they should be named differently from the standard types. They should be consistent with template arguments. For example, if you have standard string, the usual notation for template arguments is Pascal notation, not snake case. And there are some confusion with type traits. You have the well-known and used type traits today in the C++17 standard, and there are situations where it gets really confusing when you mix them up. Okay, rant over. By the way, if any of you have questions or comments, I do take comments as well, disagreements, feel free to interrupt me at any time. So what's the practical upside of all of this? If I'm not a library writer, why should I care about all these things? Well, you should care because hopefully you're using STL algorithms and data structures. So you need to be aware of these issues to make sure that you stay in agreement, you stay in contract with the protocol you have between the library designer and you as a client user. So going further, designing and exposing your own vocabulary types, and when you design interfaces, when you design APIs, you should make sure that they are intuitive and they meet the expectation of the programmers consuming those libraries and those types. Very simple concept. I think it's one of the most pervasively used in the STL, the compare concept. For example, for the sort algorithm, compare concept is a predicate, it's a function object, it's a binary predicate. Looks something like that. And you have to think about implementing such a compare concept. You have to think about the ordering relationship that you must construct for the types that you're comparing. And I go into a lot of details about this in my previous talk on regular types. Here I'm just going to skip to the conclusion in that the expected ordering relations for the compare concept is strict weak ordering. And you see here the axioms that must hold for the operation such that the algorithm actually works. And we have a definition, our first definition for equivalence here, in that if we cannot decide if A goes before B or B goes before A, then we must conclude we have an equivalence relation between A and B. If we substitute a generic comparison operation with less than, then we have the less than comparable concept, and basically the same axioms apply. So now we get to equality comparable requirement, and this is the hairy one. As per Palo Alto Technical Report or Elements of Programming, semi-regular is defined in terms of these requirements, and regular, aka Stepanov regular, not other meanings, would be a semi-regular type that is equality comparable. Yes, STL assumes equality is always defined, or at least an equivalence relation. STL algorithms assume regular data structures, and STL was written with this basic idea at its core. So violating these principles would yield unexpected results. I would recommend that you read the original Palo Alto report. It's quite lengthy, but the explanations are very good. Equality comparable is defined in terms of reflexivity, symmetry, and transitivity. And we must think about how types with operator equal should have standard semantics. For example, if you think about defining such an operator for your user-defined type, it should not have unexpected results. It should behave like strings, like integers. Should feel natural. Equality versus equivalence for types that are both equality comparable and less than comparable. STL makes a subtle difference between equality and equivalence. We've seen the two definitions here. And of course, equality is a special case of equivalence. Yes, defining equality is hard, as Alex said himself. Two objects are equal if their corresponding parts are equal, applied recursively, including remote parts, but not comparing addresses, excluding inessential components, and excluding components that identify related objects. Phew. So, yeah, and he goes on to say that this definition leaves room for judgment. Yeah. There is some help in this direction. With the new C++ standard, we get Spaceship Operator. How many of you have heard of it? Has a catchy name, almost impossible to miss it. So this comes with some help in this direction in properly defining ordering relations for types. You have quite a few strengths of ordering relationships that you can define. I would caution you to be very careful in defining weak equality, because it's a slippery slope there. And very recently, the spaceship has landed in STL itself in the library. So we have the operator defined throughout the standard library. So that's a good thing. And it will help us both use it easily, so as consume it, and it will serve as an example when we implement the spaceship operator, for example, for our types, or if we choose to. You can just opt out. If you want to get a feel for it, if you want to see some examples, real down-to-earth examples on using it, I recommend this older blog post by Cy Brand and a newer one by Cameron on the Visual Studio blog. They have examples and rationale in using it, and you can get a feel for how it feels to define such an operator for your types. Before we get too far with C++20, let's spend a few minutes on C++17. And I'm going to pick a type in particular, very dear to my heart, string view. It's an object that can refer to a constant continuous sequence of char-like objects. How many of you have used string view? About half, a little more than half. So string view, as you might know, does not manage the storage it refers to, and the lifetime management is left to the caller, the user. I have a whole talk on string view and how you can hang yourself with it. I do recommend that you watch that, just to be aware of the issues. And we're inevitably in any C++ argument, this thing pops up. String view, Rust, of course, that was the thing. String view is a borrow type. I think Arthur coined this term for string view in his blog post a few years back. String view succeeds admirably at being a drop-in replacement for a constring reference. The problem is that string view is different. We're used to value types, we're used to reference types. String view is neither. Is what Arthur calls a borrow type. And it's perhaps, it's not singular, but it's perhaps the most visible, is the first mainstream borrow type. So this would be the problem. It's too appealing, it's too catchy, too tempting to use. And that's the problem. That's why we need to be aware of proper best practices in using it. Borrow types are essentially references to existing objects. They lack ownership. They are short-lived, or at least they should be. They can generally do without an assignment operator. They generally appear in function parameter lists and cannot be safely stored in data structures or removed or returned safely from functions as any reference, basically. So you have to think about them as references. Yes, string view is assignable, but the assignment has shallow semantics because the underlying storage is immutable. So that should meet our expectations. And equality is deep in terms of being a lexicographic comparison of the underlying string. So again, I think this meets the expectations of programmers. No surprise here. When the underlying data is extant and constant, like with string view, and if you can analyze the context, you can determine if the usage is safe from its environment, its usage. And you can almost think of it as almost being regular. So if you restrict its usage to parameters, function parameters, for examples, it's kind of like it's a regular type. It's almost always safe. So not great, not terrible. But now we get to this one. Yeah. Now we get to this one. The comment was that it's very useful. True. String view is useful. Standard span, the very confusing type that doesn't exactly know what it wants to be when it grows up. So think about span as in array view, like string view, but with mutable underlying data. This is the catch. Span as string view does not manage the storage that it refers to. The lifetime management is left to the user. And it has quite an interesting historical background. It actually started in the C++ core guidelines. There are two guidelines that mention span. Use span and span p to designate half open sequences, and pro-bounds safety profile. The reason is that informal, non-explicit ranges are source of errors, as we've seen before. We've been burned by this. Ranges are extremely common in C++ code, but they're usually defined implicitly, not explicitly, by using pointers or by using offsets. So given a pair of arguments p and n, defining an array p plus n, it is generally impossible to know for sure if it's safe to dereference p at a specific point after it progresses through that sequence, because the sequence is implicitly defined. It's like an agreement, like a sort of an expectation rather than a formal specification of a sequence. This is where GSL span and span p come into play, and they were designed to explicitly state this intent in the code. Pro-bound safety profile recommends that we don't use pointer arithmetic and use span instead. Sounds pretty decent advice. Only index into arrays using constant expressions. Sure. No array to pointer decay. Okay. And don't use standard library functions and types that are not bounds checked. Okay. We want performance, right? At least on debug, we can live with some checking. So if you want to read more, by the way, all my slides have links to articles. So when you get the slides, you can basically read for a while. The GSLs or the guideline support library is a set of headers, and it includes a span header. And I think it's about 2 years old now. And if we think about the first proposal, the original proposal of standard span comes directly from the C++ core guidelines, GSL, and is intended as a replacement for unsafe C-style pointer length parameter pairs. And the quote is that we expect it to be used pervasively as a vocabulary type for function parameters in particular. So again, very similar to what we've seen with string view. This is the original proposal. We do have some automatic checkers for these guidelines. We have them in Visual Studio 2017 and 2019. Even in 2015, there's a NuGet package that you can install and get most of these checks. You have them in LLVM Clang Tidy, all the checks that start with the wildcard CPP core guidelines, and you can even combine them and use the tidy checks in Visual Studio if you'd like. The LLVM Tidy, Clang Tidy check, we have the pro-bounds array to pointer decay that checks exactly what we've talked about. And we have the pointer arithmetic check that checks for messing with pointers, of course. This is how it would look like, for example, in Visual Studio. We have these error types that we can identify in code. We can see some simple examples. You can even suppress those warnings on regions of code that you know, okay, I know what I'm doing here, kind of thing. Yeah. This is how recommendations would look like in code with inline suggestions. Might become the newer Visual Studio versions have static checking by default, and they do it in the background. And sometimes it might feel a little annoying being pestered by all those squigglies. So opinions might vary on this. I might like it. I might prefer to run them on demand rather than seeing them pop in my front all the time, but you might feel differently. So span is defined in terms of a pointer and a size. And it can have either a static extent or a dynamic extent in terms of how it's constructed. For example, if it's attached to a C-style array or a standard array. But you can attach it, for example, to a standard vector. I want to point out this templated constructor. You have expected notable functions like front, back, index operator, data, interesting size bytes, and as bytes or as writable bytes, in case you want to stream it somewhere. You can obtain subviews, similar to removing prefixes in string view or suffixes. So you have first, last, and subspan, for example. Quite useful if you want to move this sliding window through a buffer. And there have been, I'm going to focus a little bit on the evolution of the design of span, because it changed over time from the initial proposal up to the current specification in the current draft. It changed. So we're going to examine some of these changes and see if we can learn something about the mistakes we've made and if we're in good shape now. We'll see. For example, front and back member functions were added to getting consistency with standard library containers, like vector. Empty function was marked no discard, same as vector. Operator parens was removed. This was a vestigial implementation from the original proposal that had array view that was supposed to be multi-dimensional. We'll see that this was spun off as a separate proposal. And we have structure binding support to get tuples from a fixed size span. Quite convenient. But at every step in this design evolution, we have to think about WWSD. What would Stepanov do? And I think this paper by Tony, I think it's the most accurate analysis on the state of the span that was 1 year back. And I think we have a lot of to learn if we examine these arguments. For example, it's humorous too. I recommend that you read it. Overloading operators can be dangerous when you change the common meaning of the operator. We've already talked about this. We cannot give different meaning to operators that are commonly used. The meaning of copy construction and copy assignment is to copy the value of the object. And I think we now have a pretty good understanding what values should be. The meaning of equality and comparison is to compare the value of the object. Copy, assignment, equality are expected to go together, as in for built-in types. For example, if I have copy and assignment, I would expect to have equality. When designing a class type, where possible, regularity should be considered. This comes straight out of elements of programming. Okay, so far reasonable, I think. The copy is shallow for span. In terms of it copies just the pointer and the size, so it's not deep. We could make it. We could make the comparison deep, and actually the original proposal was implemented in terms of deep comparison using the equal algorithm, just like string view. So the original proposal was very much akin to string view. However, string view can't modify the elements it points to because the underlying character sequence is constant. So shallow copy for string view, it's something similar to copy on write. We're used to this pattern. But is span a value? Do we need a deep compare? Do we really need a deep compare? Span is trying to act like a collection of elements over which it spans, but it's not quite regular. Basically, span has reference semantics, if you think about it, in terms of how it is intended to be used. But it sometimes masquerades like a replacement for some kind of a container. It's easy to get confused. Deep comparison also implies deep const, like logical const, extended to all its parts, like we defined earlier in terms of elements of programming. All parts that constitute its value. For example, all parts that participate in equality and copy. Deep equality means the value of a span are the elements it spans, not the pair pointer plus size. That's what deep equality means. So if we want span to act as a lightweight representation of it over the elements it represents, we need to have shallow comparison, just like smart pointers, for example. If you think about unique pointer. Shallow const implies shallow comparison. But shallow comparison might be really confusing to users because it's different, for example, from string view. So if you're accustomed to a type that you already have and you already use, it should get confusing. Yes? Yeah. The comment there was that shallow equality would be useless as well. True. For span, it would be useless. So in the end, the decision was to actually remove equality altogether. So now we're in trouble. Go ahead. Yeah. Um, for practical reasons, because yeah, as a drop is a drop-in replacement in the signature. Yeah. 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 Exactly. 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 Yeah. I'm gonna rephrase that for the recording. Marshall's comment was that as we designed span over 2 years, I think, yeah, we realized we made some mistakes, and that shallow equality would make no sense, and that deep equality would be just weird. So the sensible thing to do is just remove the operator altogether, and that things would have been much more easy for us in designing the type and in using it if the underlying buffer would be constant, just like with string view. Then we'd have uniform expectations from the users because they know string view. They would understand how span works. But then again, for practical reasons, like Titus commented, for practical reasons, you do work with pointers to immutable buffers. And if you want span to succeed in terms of actually being used, sometimes you have to just accept that you have to make it work with with mutable data. So then you get in trouble. So just removing the comparison altogether, in that making span from a regular type, making it from a regular type that looks weird, making it semi-regular, at least it's honest in terms of what it can do for you. So yeah, it is difficult because you have to meet practical requirements on, do you actually want people to start using it, or you want just the purity of a properly designed type that nobody will use. So, but again, we have to strive for at least coherent thinking there. So stay away from madness if we can. So it's a strange beast. So you can reasonably expect it to be a drop-in replacement for array and vector. And that happens to be mostly the case. You can attach it to such containers until you try to copy or change its value. And then it stops acting like a container. So you get into trouble. So it's semi-regular, like Titus pointed. It's a weird beast. Again, summarizing non-owning reference types like string view and span, you need more contextual information when working with them to make sure to understand the context of an instance of these types. So you need to consider shallow copy, shallow deep compare, const mutability, what equality means. So it has reference semantics, but without the magic that makes references safer. For example, lifetime extension. So you don't get lifetime extension for string view. A very simple example there. You can see how you can easily get burned, especially for string view, because you get small buffer optimization, and for smaller strings, it might fool you in actually working. So basically, you don't get all the magic from lifetime extension of regular references. And detecting dangling references, there is a clank tidy check, bug-prone dangling handle. And by default, it checks for string view, but it has a configurable option to change the handle class to be whatever you want. So it could work with span. We do have, since last year, we have the lifetime profile. And This is important because it turns out it's easy to convert from string to string view and from vector array to span. And dangling is almost the default behavior there if you're not careful. So you don't need some tool help there until we get properly educated, at least. For example, we have the W lifetime flag that was experimental in Clang, and it helped point out dangling references, string view references to temporary strings, such as in this simple example, but you can imagine a function returning a string or something more complicated than that. For example, imagine a ternary operator that has string literal on one side and something like a string on the other side, and you have things constructed that are not obvious. So you get dangling references to temporaries there. And very recently on Clang trunk, available in Clang 10 in the spring, we'll have a new check on by default, W dangling GSL. And that will warn exactly on these situations, initializer pointer member to point to temporary objects whose lifetime is shorter than the constructed reference there. So I'm glad to hear that this will be on by default in Clang 10. So it will detect this. So we're growing up, going from experimental flags that nobody knew about and nobody used to something that will be production ready. And we get rid of a whole bunch of false positives that we had with the experimental W lifetime flag that yielded a lot of false positives, and people didn't quite like it. I'm hoping, right now it's not implemented, so it's not in Clang front yet, but I've spoke to people that are involved in this, and there is a PR for span, and I'm hoping to make it in Clang 10. So I'm still optimistic. It's a little bit more difficult than the string view type, but I'm still optimistic that we'll get this in spring in Clang 10. Simple rules for borrow types. They must appear, as we said, only in function parameters or for loop control variables. If you want to make an exception, for example, for returning these kind of things, you must be very careful in documenting what you're returning and the expectation on the caller to be careful on the usage. You might think about documenting the API or inventing some crazy looking custom C++ attributes, like, trust me on this one. But either way, you have to be really, really careful if you do that. If you're thinking about returning these kind of things, I would recommend against it. Compiler support, right now, span is only available in the libc++ library. Sad, in my opinion. Available since Clang 7, and it has evolved. For example, if we look through the Clang versions, we see basically the evolution of the spec of span, the proposal itself, from the initial removal of comparison operators, usability enhancements in first, last, tuple, structure binding support, and S size. So we see the whole evolution of span in the experimental implementations. Span is going to evolve even going forward beyond C++20. For example, there are proposals for range constructors for span and string view. We're going to see how those evolve. And there's even a proposal to use span of Charty as a stream replacement. If you can't wait and want to use it now, you can use Clang 9 with libc++, or you can use an independent implementation by Tristan Brindle that is available on GitHub, or you can even use the one from Chromium that is even bounce check, like some people like. So there is a caveat that Timur likes to call the 5 phases of joy. I think you can guess what the C++ feature is in this drama. Yes, it's span. The problem is that it lacks a feature test macro. And you could think, can I use hasInclude for that? Because it's a new header. No, in libc++, you get all the headers. It's implemented. But they turned up empty if you select the wrong C++ version. So that intrinsic cannot be helpful. So yes, the reason you care about this is if you want to use an early implementation of span that has the same API, and you want to just change the namespace or change the name once you get it in your fully compliant C++20 compiler. So that's why you would care. Double or nothing, anyone? A span of string views? This combines my two favorite pet peeves in one glorious disaster, as I like to call it. If you think about this, you can reasonably expect some of these arguments to end up in some POSIX function or some system API function that actually expects null-terminated strings. So, yeah, don't do that. Beyond span, things where I consider to be more interesting to examine further is ranges like stride view, slice view, sliding view, cycle view, chunk view. These would be interesting areas to explore in terms of the ranges STL. And I think we might get much nicer implementations in terms of actually using ranges. But you have to embrace a whole other way of thinking about your algorithms. Other dimensions, like I said, the original span proposal used to be multidimensional as well. This has been spun off in two different proposals, I think, or one. MD-span and two. MD-span and MD-array. There are already implementations. You can hear more about it in CppCast with Bryce. And we have an experimental implementation. They're all about defining data layout in memory in terms of using it. It's useful for high-performance computing and graphics, and defining custom layouts that are amenable for traversing in a particular way that is efficient for some scenarios. So this would be a much more advanced territory. My call to action to you would be that you make your value types regular. The best regular types are those that model built-in types and don't have dependent conditions. Think about integers, standard string, vector as your primary examples of well-defined types. And for non-owning reference types like string view or span, yes, sometimes we need these kinds of tools. You do need more contextual information to be able to reason about those, and try to restrict those to be semi-regular, to avoid confusion for your users, to be honest. So this would be why I care about short lifetime and why I care about regular types. Thank you. Questions? Yeah, if you could line up to the microphone would be easier, because I don't have to repeat the question.
With string view,
Yep.
for example, it seems like the intended case for usage in many scenarios, as you'd said, was as a function parameter, at which point you manage to achieve whatever results you want in some generic misdirection through implicit conversion. Rather than writing some templated function that takes all the things you wanted to view, you allow implicit conversion to take that stance for you. In that particular regard, regular references, non-const references, don't have the opportunity to be implicitly converted. So your options at that point are by value or by const ref. I'll ignore R values for the time. My curiosity is, it seems like the way that span is playing out here then, that if you were to pass it as a parameter, if you pass it by const ref, you lose the mutable capabilities that it's bringing to the table, because operator square brackets is
excuse
const.
me, do you mean by
not?
pass a const ref to a span?
If I were to allow
Why would you
a
do
function
that?
signature to have a const span reference.
Why would you do that?
I
Why
don't-
wouldn't
I
you
don't-
pass it by value?
And again, my point being that there seems to be, for the first time, an expectation, really, that the language is saying that I should be only passing by value. In many cases, we've said the compiler will help us. I'll allow you to jump in. I see you raising your hand.
For string view and span, I think the expectation is to pass them by value.
I agree that that's the
Because
expectation,
it's cheap.
as it seems.
Because it's cheap.
Sure.
You don't have any reason to pass it by reference. Think about, it's arguable, for example, even for, I've seen this argument being made for shared pointer, for example. passing by reference versus passing by value, because you want to avoid the atomic increment and stuff like that. But for stuff like string view and span, there is really no cost in passing by value.
And I don't challenge you there at all.
You just basically copy two integers.
My curiosity is if it would have just been easier at some point to just define with concept setups a spannable, rather than trying to dance around all of this stuff that seems to indicate that I can or cannot own but change what the values are. Again, it seems like we have a lot of template stuff that allows us to do that, and we just tried to beat the template stuff and defining it inline in .h's by introducing an implicit conversion to a generic type. I'm just trying to figure out, it seems
I see the
messy,
role as
yes.
a little different. String view is meant more like a glue code. For example, you put it in your interfaces as a glue code between different types of strings. For example, you have different types of strings in your application. You have your standard string, you may have your UI string or some character-like sequence that is convertible to a string view. So it would act like a duct tape between incompatible types through the fact that it gives you convenient conversions, as opposed to span, that it's more like not meant as a glue code, but more meant as formal specification. I'm expecting this to be a memory range, as opposed to giving you 2 pointers or a pointer on a length. I'm explicitly saying this should be a range, and you should traverse it like a range. So I find although they're meant to be used in function parameters, I find their rationale a bit different, in my opinion.
okay.
So I would expect people to pass them around as values, but not store them.
Sure. Time, I guess, will introduce comfort with that, I suppose. A second question, if you don't mind.
Sure.
You were talking about replacing pointer size t tile. I guess I'm going to think of them as CAPI interactions.
Yeah.
Would the expectation be that I would always then be writing an inline wrapper that forwards the span and breaks it up so that I can match any CAPI signatures that require two?
You have the data member that
Sure.
you can get the pointer back and the length.
Right, but if I have a third-party library that's written in CAPI and it only takes pointer and size,
You have to split it manually.
Right, that's what I mean. So the expectation is that I'll have to write a manual.
Yeah.
Okay.
It doesn't have an operator or something that decays to a pointer.
Is the future intention to eventually attempt to mitigate needing to do that at all with this
I don't
introduction?
think so. I don't think so.
Okay.
I think the intent is to be explicit about using it.
Sure.
Marshall, care to comment?
Multiple pieces. Right. Wasn't there a thought about like using curly braces to allow you to allow for some converting constructor to occur with multiple parameters if you wrap them in? Sure.
Yeah.
Sure. Operator stood tupled pointer. Sure, but we have those ways to.
Yeah.
Sure. Sure.
You don't have something that expands like a param pack or something.
Well, some of the fold expressions seem like there's some wizardry that could occur there. But regardless, though, I'm just curious about the span. I know the Valorey stuff provides you with the opportunity to do slices and other things like that already. Does it seem like with some of those future things you were talking about, we're going to be inventing something that already exists but might not be used very much?
The ranges that I mentioned, like stride view and
like
chunk
view and slice view, etc.
Those are being considered. My knowledge is that currently there's not even a paper per se, but they're considered to be added. But those are related to the ranges library.
Sure.
So when we talk about span, we talk about in the context of your everyday functions, or your current algorithms that take iterated pairs. If you talk about ranges, that's a whole different set of algorithms. So you have to fully embrace that route. Yeah. Exactly. Yeah. Exactly, yeah. Or I might want to process it at compile time.
Sure.
I'm gonna just quickly rephrase that for the camera. Marshall was commenting, following your question, that string view and span are meant as low-level facilities for performant access to memory, for example, for span, or for low-level string processing in terms of string view. You can even do compile time processing on compile time strings, as opposed to the ranges, span-like things like stride and chunk view and slice view that are meant to be much more general, much more abstract concepts that you can use over anything, basically, not just raw memory. And those are also can be lazily evaluated, and you can run special views over them, and they're much more abstract, much more generalized concepts.
Sure. So,
No problem.
somebody preempt me if I'm...
I have to quickly end the session because we ran out of time, but I will take comments and questions afterwards. Thank you very much.